So today we want to look at classification. Classification. And I believe that about half of you will use classification in your research, in your longest. So the classification we are going to do, is going to be very important towards anything else, not only for this course, but also for your long essay and your thesis that you'll be doing. All right. Now, you remember that in linear regression, we assume that the dependent variable is quantitative. In many situations, though, the dependent variable can also be qualitative. Now, when I say qualitative, I mean it is categorical. And so we are going to consider how you can estimate a model when the dependent variable is categorical. And this is known as classification. Okay. So in classification, your goal is to predict. And please, if you are taking notes, write this down. Okay. You see, sometimes when you write it down, like I'm just saying you should write down, it helps you when you don't even understand. Later point in the lecture, you get it. So you will notice that you talking about the word predicting the probability that an observation belongs to a particular class. For example, right now, if I close my eyes and I touch the head of you, what is the probability that the person is a male? What is the probability that the student I will touch the head is a female? The likelihood, the chance is important. And we know that the chance is going to be fully 100% or not. So it's going to be in between. And this is what, classification is looking at. It behaves like a regression, but instead of saying that when I close my eyes, I will get a male. You can't. You can't say you will get a male, but you can say that the probability that I will get a male is this. So you assign likelihood to the occurrence. Unlike regression, where you say that if I do this, I will get that. So in classification, we use something known as a classifier. The classifier is actually the model itself. And there are many classification techniques or classifiers, for qualitative dependent variable. There are many. Sometimes, don't wait for me to get to the deeper side. When you don't understand the beginning side, you ask. It helps you to be able to get to the deeper side. So we are going to look at some of the methods or some of the commonly used classifiers for undertaking classification. One of them is logistic regression. Now, you're going to even understand that why do you even call the thing logistic regression when we are doing a classification? There is also discriminant analysis, quadratic discriminant analysis, naive Bayes, k-nearest neighbor. All of these are classifiers. You will be using, most of you will be using logistic regression and k-nearest neighbors. Most of you, and naive Bayes. But we're going to start with the logistic regression, okay, because it stands for the generalized linear models. It serves as a foundation for the generalized linear models. Later, we look at more computer-intensive classification methods, the additive models, the decision trees. So we'll look at decision tree classifiers, random forest classifiers, gradient boosting classifiers, support vector classifiers, and things like that. Okay. But today, let's understand classification first and look at logistic regression. So let's look at situations that will warrant a classification phenomenon. You arrive at the emergency room with a set of symptoms, and the symptoms could be attributed to one of the three medical conditions. Three medical conditions. So we are not talking about one, but three. And so you could be suffering from any of those three medical conditions. Which of these three medical conditions do you have? Or does a person have? Which of them? That the likelihood of getting that medical condition is a classification problem. An online service, okay, you have to determine whether or not a transaction is fraudulent or legal. Because in a bank, for example, so many people are doing transactions every day. How do you know that this particular what would be the way to flag? Oh, it's not fraudulent. Oh, it's fraudulent. Oh, it's not fraudulent. Okay. Based on the user's IP address. So there are certain factors that will determine the probability of it being fraudulent or legal. You use the IP address, you use the past transaction history, and so forth. All of this will tell. Another thing is based on DNA sequence, from a number of patients, okay, patient with and patient without a disease. A biologist can figure out which DNA, which deoxyribonucleic acid mutations are deleterious, that is disease-causing, and which of them are not deleterious or are not disease-causing. Now, which of you can give me an example again of a classification? I've given you an example, but which of you can give me another example that comes to your mind? Anybody? Just raise your hand and tell me, because that is the only way you learn. Because I've given you 3 examples, you should be able to give me one. Yes, Wallace.
Driving without brakes.
So you got to always mention the classifiers. So you got to mention the classes. That is a mention without grades. You have not told me the groups. I just gave you an example that you get into the class, someone has failed. You want to know what's the likelihood that the person is a male or a female? Cosmos.
Yeah, predicting customer churn. So whether the customer will churn or not.
Very good. That's a typical good example. What else? All right, just like in a regression setting, in classification, we have a training set and then a test set. Okay, we have a training set. We want our classifier to perform well, not only on the training, but also the test set. So there will always be a training classifier and a test classifier, just like in a regression. Now, there are some categorical variables that take values in an unordered fashion, unordered set. For example, when you take the eye color, what is the probability that this person eye color is brown, blue, or green? This is a classifier. Remember that this is not just binary, like email being a spam or not a spam. No. You can also have 3 categories. Now, if you have the predictors or the independent variables, and then you have the dependent variable, the qualitative response. If they take a value in the set, that set that I just gave an example of, then the classification task is to build a function which is CX, that will take an input, a feature like X, and then will predict the probability of having a Y. So the function becomes that f of X is a member of the function, okay? Or C of X is a member of the function. Normally in a regression, we normally write f of X, but here we are writing C of X, where the C is sort of representing classification. But we are not just looking at the thing happening, we are looking at the probability of the thing happening. So he spoke about whether a customer will churn or not churn. Really, that word whether is indicating the probability that a customer will churn. You see, whether a customer will churn or will not churn is 0 or 1. But then you got to find probability. So under what probability will it be one? You can say that when the probability, anytime it is 50% or more, then the probability of it happening is one. And anytime it is below, then it's towards the zero. So the probability of it not happening is zero. So we use probabilities that an independent variable belongs to a particular category or it does not. Probabilities. It's more valuable to have an estimate of a probability than an insurance claim is fraudulent. So if you say that, oh, this insurance claim is very fraudulent, you can't just say that. But you can say that it is probable that the insurance claim is fraudulent. Now, why is that second one better than to say that the insurance claim is fraudulent? Who can tell me? Why is it better to say that it is probable that the insurance claim is fraudulent than to say the insurance claim is fraudulent? Winnie?
I think it's because you cannot be 100% certain.
Yes, but there's also another reason why. That word, you cannot be 100% certain. I mean, you can also be 100% certain. You can do the analysis and be 100% certain too. Yes, Judith.
Doctor, I think may not be.
Oh, your line is breaking. Sorry, your line was breaking. Say that again.
Can I say it may not?
Sorry, I can't hear you at all. Let's go to Emmanuel.
Yes, sir, there could be false positives in our work.
You think that people here understand what you just poured out? Explain well what you mean in simple terms for them.
Okay, so sometimes when you run your classification model, the answer could be it can give you a yes, but in actual sense, it's actually a no.
Use the example I just gave you here. Use the insurance claim fraudulence to discuss your point.
Okay, so for example, the insurance fraudulent, there could be an instance whereby there's no fraudulent, but the model will predict that there was a fraudulent. So because of that, we can always you can that's why you usually use the probability.
Okay. All right. So let's take an example of this default data set. You have a student, whether the person is a student or is not a student is here. You have the balance, the credit balance of the person. You have the income of the person. So this first person, his income is $35,458. And that person's credit balance is 56. This person, the income is lower, 12,000. That person's credit balance is what? Is higher. 723 is higher. Now, if you check, the first person is not a student, but the second person is a student, right? The second person here is a student. So just between these two, is there a kind of a trend that those that are students have lower income and higher credit balance? Could that be the case? We'll see. Let's go to the next one here. This person is $41,000 income. You can see that the credit balance is slightly higher. He's not a student. And then on and on and on. So when you look down here, this default is the qualitative response variable. It is a dependent variable. It's a binary dependent because it's a yes or no. But this student is not a binary dependent variable. It is an independent variable. It's a dummy variable. It's a binary independent variable. Okay. So what are we interested in here? Well, we want to predict whether an individual will default on his or her credit card balance payment. You got to pay. You have exceeded the amount by what? By 723. You're a student. You are using the thing too much. Could that be the case? Well, somebody too is making a lot of money here, and still he's also exceeded the credit balance. So what can we say? Could it even be that the students are not? And that is key. Yes, Abigail.
Go. Good morning. And please, can you elaborate on the question you asked earlier, the one that Ima answered? I'm trying to wrap my head around it, but I'm not really understanding the answer he gave. So can you please elaborate on it?
Elaborate on what? You asked him. He was the one who said it.
So can I re-explain?
Yes.
Okay, so when usually you build a model, you're not always 100% certain. There could be possibility that you will have false positives and false negatives. False positive is when there's a legitimate transaction, but the model predict that is fraudulent. And with the false negatives is when there's actually a fraudulent, but the model predict that it's legitimate. You understand?
Yeah, so like the question was, why is it valuable to know the probability of an insurance claim being fraudulent than knowing classifying them? So where does your answer fall into it? Because so if they are going to be false negative and false positive, so it means like, okay, it's making sense now. Thank you.
All right. Good. Now let's continue. So what are you going to use to determine whether a transaction is fraudulent or not? Or sorry, what are you going to use to determine whether a student or non-student is going to default on his or her credit card balance? Well, there are two factors here. One, we are going to determine whether we are going to use the person's annual income and credit balance. That's what we are going to use. The annual income of the person will determine it, and also the credit balance. So that's what they use. That's what the banks will use to determine whether you will default or not. Now, the default data set is displayed. I think I gave you the default data set as well. I want to believe I did give you the default data set. Well, if you don't have the default data set,
Yes, you did.
I did. Okay, good. If you don't have it, I can give you. But then I did give you. You know that default data set, it goes really deep. It goes all the way to 1,000. If you check, let me just show you a little bit of it. We'll come back to that one. So this is a default data set. Okay. I just ran the first code and it shows all of them from 0 to 99999. That's 10,000. Okay, 10,000 people. And then you have default or not default and things like that. We'll come back to this data set. So when you look at this default data set, we are showing here the relationship between income and the balance. And when you check it carefully, of course, we are classifying the income and the balance. And you will notice that in this very example here, the one on the left, we are plotting the annual income and the credit balance for part of those 10,000 people. And this side here, we have two box plots. One is this, but check the box plots. We have measured the box plots and we've looked at the group of default versus non-default relative to the balancing, and then the default versus the non-default relative to the income level. What is one quick thing you can see here? You can see from here that those individuals that are defaulting, they have a high balance. Do you see that? This is the median of the box plot. They have a very high balance. And then the individuals who are not defaulting, on average, they have a very low balance. Now, when you go to income, the individuals who are defaulting, the reason why, of course, they have a high balance is because they don't have a lot of income. So their income is low. If you check the median value of the income is lower than those who are not defaulting. Those who are not defaulting, they have some money already in their bank account, so they are not defaulting the credit card balance. So this is a picturesque understanding of the data in the first place. Okay, now, so individuals who defaulted tend to have a higher credit card than those who did not default. And you can see that here, higher credit card balance. So the legend says the box plot for balance clearly shows that individuals who defaulted tended to have a higher credit card balance. The income one shows those who defaulted had an average income that is a little bit lower than those who didn't default. I've said that already. What are we trying to do? We want to build a classification model to predict default. I would say to predict the probability of default for any value of the balance and any value of the income. That is the focus for today. That is what we want to build. That is what we want to engage in. So how do you go around this? Well, suppose we are trying to predict a medical condition, because it's important for you to ask, why didn't you use a normal regression? And now we are going to talk about classification. If you are predicting the probability of a particular patient in an emergency room on the basis of the person's symptoms, you want to now predict what medical condition the person is having. We could let Y take on the following diseases. Looking at the symptoms, the person may be having a stroke, may be having a drug overdose, or the person may be having epilepsy. If you go and use OLS, least squares, you can use that to fit the model very well. But if you check the representation, Y implies an ordering on the outcomes. It implies that Y is, has an ordering. It puts the drug overdose here in between the stroke, number one, and epilepsy. And it is insisting that the difference between stroke and this drug overdose, the difference between the 1 and 2, is the same as the difference between drug overdose and epilepsy. But is that the case? No. There is no natural way to convert a qualitative response with more than 2 values into a quantitative response that is ready for a linear regression. You see that very soon. Because linear regression, as the name sounds, is linear. Is linear. But qualitative variable is not looking at, the dependent variable is not looking at linear, it's looking at 0 or 1 or 2. So using OLS is a bit dangerous. It's not a bit dangerous. You see graphically very soon that it is dangerous. But if you have a binary response variable, not 3, as we looked at before, we could use a dummy variable approach. So let's assume that we have 2 possibilities for the patient. Instead of the first and the second and the third, the situation is that given the patient symptoms, the person may be having stroke or drug overdose. Okay. So the binary response variable, the Y, the response variable is 0 if the person is having a stroke, and it's 1 if the person has an overdose. Now, we can fit a linear regression to this binary response. We can. And we can also predict that the response variable is a drug overdose, provided that the predicted value is greater than 50%, and that it is a stroke if the predicted Y is below 50% or 50% or less. We can do that. We can do a linear regression. That's all I'm saying. We can do a linear regression. But there's an issue there. You see, here we are using a dummy variable, 0 or 1. Even if we flip the above coding, linear regression will produce the same final predictions, whichever way you do. The outcome is going to be the same. OLS is having an issue. Now, the linear regression might produce probabilities less than 0. But remember that this thing doesn't say that it should be less than 0. Less than 0 means negative. It can also produce probabilities greater than 1. Therefore, we need to go back and look for a better method that will settle the values between 0 and 1. Not above, not below. Logistic. That's the one that can do that. And when you go to the credit card default data, we'll see that. We are going to look at all of this there. So please, if you can, follow me as we demonstrate the power of this in our credit card data set. So this is a data set. As usual, we have all the usual pandas, NumPy, Matplotlib, stats model, LAPR formula. All of these things are common. The data set is default. If you have put it in your working directory, we are going to fit a linear regression model to show why OLS is not good. That's it. That's the first thing. The first thing is that the default data set, okay, for example, let me show you the default data set before I show you the encoded one. If I go here and then I run this, oh yeah, it's rather data, not data one. So let's do this one. So watch it carefully. You can see that now here, the dependent variable, which is default, is binary. It's not been coded. So we can use a one-hot encoding to code it. And then there is also an independent variable, student, which is not coded. These kind of English words are going to disturb. So the first thing we want to do is to encode them. So when you come here, I create another data set known as data one. Instead of data, I call it data one. And then I say that I want you to give me a new data set from data one, but make sure that you are picking it from the original data and ensure that the default data has been coded. So drop anything that is categorical nature of that. So I do that. Let's run that. And boom, you have this. I didn't touch the independent variable, the student. My interest is the dependent because we are focusing on balance and income. So now you have the data set. You can look at the head of the data, okay, the first 3 rows of the data, or you can choose to look at the first 5 rows of the data like this. Okay, good. Now we need to specify what is a dependent variable and what is the independent variable. The dependent variable is what? Who can tell us? Quickly. What's the dependent variable? Default. But watch the way I've defined a dependent variable. Because I've coded it, and then the default is yes, it means that whatever it is 1, it is what? It's default. And whatever it is 0 is non-default. So this one is no, it's not default, it's not default, it's not default, it's not default. Okay. So the dependent variable should be collected from the data one, and it should be the default yes. Now, this is just one independent variable, the balance. We are using just the balance. We can add a constant when it can fit this regression model. Just for balance, this is a simple regression model. Normal OLS. How do we know it's OLS? We've specified it here. Okay. So in here, you can see that there's OLS. We can print the results. But we are going to also prove that the predictions are negative. If we are going to use this data, it's going to predict a negative value, which we don't want. We are going to prove that. We are expecting the values to be between 0 and 1, but it's going to give us some values, and you're going to see that very soon. Let's get a predicted value. Suppose I want to predict. So this is a Y predicted. Okay. And define it as predicting, suppose we get a balance, we drop in a balance, which is the X, into the model. What will Y be like? Print that one too for us. You're going to see that. And now we're going to even plot. So plot the predicted probabilities against the balance. The predicted probabilities against the independent variable. And then let's see. Show clearly the plot of the balance. This X is a balance and the Y is a predicted. You showed all of the variables. And let's see the first result. Now check the first result. The R square is very small, 12%. That's the first danger. Second danger. You will notice the constant is negative. The p-values are all significant. Check it. They're all less than 5%. They're all significant. So you'll be tempted to say that then everything is good. Now, the independent variable for balance is this. Remember, it's in thousands. Okay. Now, look at the conditions we had for the predicted dependent variable. You see, predicted dependent variable, look at some of them. One of them is not negative. We don't want that because we have already indicated that this value is going to be between 0 and 1. And now we have another one. So this is observation 4. Observation 4 is negative. Observation 9,999 is also negative. Wahala. We decided to do the drawing. We remember we showed it there. And when you look at the drawing, we are predicting. Now, on here is a probability of default. It's supposed to be between what? 0 and 1. Okay, so here we have the 0. Okay, 1 must be way up somewhere here. Anything, this line, this is a fitted line. The fitted line should be between 0 and 1. It should be only up to here. But you can see that it has exceeded. It's gone way down. Okay, now it's gone past that, it's going into negative. It's gone into the negative area. So what is this saying? It means that if you take this line, for example, it means that if your balance is 500, the probability of defaulting is not going to be 0 or 1. It's going to be negative. That doesn't make sense. And here we have the wahala. That is why regression is not the best. Who is not clear? Who is not clear? If you're not clear, you say, I'm not clear. Now you can use the same example using scikit-learn. Remember, we didn't use scikit-learn, but you can use scikit-learn regression with the part C. So you can come here, the same thing. Okay, nothing is different, just that we are using scikit-learn. So you have the pandas numpy. This time we are adding the part C, and then we are going to use scikit-learn. You see, we didn't do that before. We didn't use that before. Now, sklearn is here, but when you go to the previous one, there was no sklearn. We're just using the, what do you call it? We're using the stats model to do the prediction. So how does the sklearn actually show? Again, the same thing. When you go and run it, you're going to get the same thing here. The same graph, the same everything. And that becomes a wahala. Regression is giving us problems. Okay, we'll come back to the rest of this because from here, let me just put in, here is another point that we'll come to and talk about. Let's go back to the graph, the results, the slide. So linear regression is not good. So when you actually run linear regression, the values are supposed to be 1 here and 0 there. But the line is crossing the 0 to negatives. And the line, if it goes up, it can go up and it will cross the 1 as well. Linear regression deals with values that are up to infinity. Linear regression is used for data that is profit. You see, profit, when you're doing profit, you can also have a loss. Okay. A company can have a profit and a loss. And loss is negative. So linear regression is good for that. But it's not good where the values are just 0 or 1. So we got to use something else. And that something else is the sigmoid function, the S function, the sigmoid function. What is that? So here you have the predictor probabilities of the default. And this sigmoid function is the same as a logistic function. That is what leads to the logistic regression. So the logistic regression will make sure that the values are going to be between 0 and 1. That's what it's going to say. Purely 0 and 1. And so at the 1, it's asymptotic. At the 0, it's asymptotic. It doesn't cross the axis, but it is sitting on it. All the probabilities are lying between 0 and 1. Linear regression is not estimating the probability that y can be 1, given x. It's not doing it well. Logistic is doing it well. And so the first way or method of estimating a classification model is using what? A logistic regression. Is there a classification method that is truly suited for qualitative response? Absolutely. That is a logistic regression. But logistic regression is not the only one that is used for qualitative dependent variable or qualitative response. We'll later look at other classification models just as we have indicated. So let's go back to the default data set. Question. The response variable in the default data set, it falls into one of the two categories. Either a customer is a credit card user is a default user or is not a default user. And you can see that. So instead of modeling this response variable directly, we use a logistic regression to model the probability that y belongs to a particular category. The probability of default giving balance, or probability of default giving income, or probability of default giving student, any of them. But let's deal with balance first. The balance one is written like this. So the probability that this chap is defaulting, that is yes means defaulting, giving balance is written like this. So it means that for any given value of balance, a prediction can now be found for default. You can know, oh, you are going to default. If I look at your balance, oh no, you default. Because it's and that you default is you default in terms of probability. Not that you default for defaulting sake. You are defaulting in terms of probability. So you are likely to default. That's what you actually mean. So let's take, for example, one might predict that default is yes. That means a person is going to default for whom the balance is above 0.5. Alternatively, the company can be very conservative and say that, let's bring the balance down. That 0.5 there, nobody can reach, I beg, bring it down. Then we say that, okay, now 0.1. 0.1. Anybody who is balance is, 0.1. That is, when I say balance, I'm talking about the probability of balance. It's 10%. Okay. Because as for 0.5, many people, the probability of balance being 0.5 or 50%, you're going to get a lot of people there. But 0.1 is great. At least some will not do it. Some will default. That is being conservative. But the first one is a general. Yes, Wallace.
Sir, can you use the table just before this slide? The last one, the default was yes. Can you use that to explain
this last
default?
one?
Yes, it is. The default is yes.
Yeah. But remember that this is not the predicted value.
Okay.
This is not the so what this one is saying is that this person's balance is 15, blah, 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 blah. And the default is yes. Yes. So it means that this person, given the balance, the person is making a lot of income though, but given the balance, that person has defaulted. But you can't
Okay,
take
so
only one person. You are taking the entire data. That's why you call it training data. You're taking the entire data. Okay, now if I bring another person, what is the likelihood that that person will default? So I'm interested in the model, not the individuals. Are you with me?
yes, sir.
I
Yes,
use
sir.
this data set to create a model. And now that I have the model, is a model I'm going to use, and then I bring a new person who has never seen this data. And I am now giving the model, I drop this new person. This new person's balance is what? Is 70,000. Will this person default? Yes. What is telling us that? It's not this data is a model. That is telling us that. Ope, are you with me?
Yes, sir.
How should we model the relationship? How do we do the model relationship between the probability that a person is going to default, given the person's balance or given the person's income or anything? How do we do the model? Well, we can have a lot of class factors. This is how we do the model. It's going to get a little bit exciting, so pay attention. Y is 0 if you belong to class 1, that is default, non-default. Y is 1 if you belong to class 2. Now, assume that the probability of defaulting given the balance, okay, probability of defaulting, yes, 1, given the balance. If we assume that, then if we were to use a regression, we would get this value, probability that X belongs to the model is going to be beta naught plus beta 1X. We know this already. The normal simple regression would have used it. But we saw in the figure that for balances
Please,
close...
Can you repeat that?
Okay. If we were to use a normal regression, we are going to get this. Now, this P, watch it. This P of X, okay, is saying that the information you are seeing here is linear. That's what regression will do. Regression will set it up as a linear model. Now, this linear model here, we saw that if we were to run the model as a linear regression, the possibility of having negative values for the predicted value, for the default, is possible. You can have more than 1, and you can have more than less than 0. We saw that. So, but if we were to do regression, this is how regression would have done the whole thing. Now, I've put P of X here, but remember that P of X is the same as this. So another way of writing the P of X is that the probability that a particular person is going to default, that is a 1, given that person's balance, okay, blah, 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 is equal to beta naught plus beta 1, blah, blah, blah. So if I was to do a normal regression, this is it. Guys, when you are doing your long essay, okay, you have to write the model. You have to write the model. When we come to the practical one, I'll show you. This one is not the actual model because I'm not using the, okay, let me just go back. Let me just go back here and do. So I would have, let me just go back and write it properly. So I would have said that the probability that Y is equal to 1, okay, and what is the Y here? The Y is a yes if the person is defaulting. Okay, so the probability that default is present, that's what this one is saying. The probability that default is present, given balance, okay, now I'm writing it properly. Given balance is equal to beta naught plus beta 1 into plus multiplied by balance. You are specifying a regression model. So this is a specified regression model. If I was doing a normal OLS regression, this is how I would have specified it. But this is a problem. We've seen that already. Because we saw that if the balances are close to 0, what this regression would do is that it will predict negative probability for the default. Simply because you are close to zero. Because it's a linear regression. A linear regression is a straight line. There's no limit. It can go negative infinity, positive infinity. See that thing? And if it sees that the thing is negative, it will show negative. And then when it senses that a person has got very high balances, it will make it even exceed 1. Because linear regression is not thinking about the parameters of between 0 and 1. And guys, if you run this thing, you see it. You see it. And we saw an example of that. We saw the predicted value, if we can remember. The predicted value, some of them were negative, some of them were positive. So we need a function that will force us for the values, this one here. Let me use a different color. We need a function that will force this value, okay, this dependent variable, the probability of, defaulting, to be between 0 and 1 per. There are many functions that can do that. But we are going to use the logistic regression, the sigmoid function, the logistic function. Sometimes some people call it logit. But that is what we are going to use because linear doesn't work. And please remember that the logistic function is also not a quadratic. Quadratic is this. Linear is that. Logistic is this. You see the difference? So that is limited. Logistic is a kind of truncation at the top, truncation at the bottom. And that is what we are going to use. Mami, do you understand now? So this is a sigmoid function. This is a general sigmoid function. Now, this sigmoid function doesn't come from business schools. It came from quantum mechanics. It came from physics. They use it to do a lot of things in physics. But now, it's been a function that has helped a lot of people, to deal with probabilities, because it's a function that is able to handle probabilities, because probabilities is between 0 and 1. And also, anytime you are doing something that is in percentages, you can use this sigmoid function. How do you write a function? You see, now you have to know a bit of mathematics of how to write a function. Well, the function is written the same way you see at the top there. Watch it. You have sigma z. I mean, this one is going to confuse you, so I'm not going to focus on this. But I want you to just know that it is 1 divided by 1 plus the exponent raised to the power negative z. This z is an equation that you are dealing with. That is a z. That is a regression equation the OLS is trying to handle. Don't worry, we'll give it a proper equation right now. But just know the graph, how it looks like. You see, the way the graph looks is telling you clearly that a function is never exceeding. Now, when you bring it into the regression framework, the z, I told you that the z is this one. Watch it. The z. The z is that part here. This is a part. Yeah. That is actually the z. So remember that the function before, it was 1 divided by 1 plus blah, 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 blah. And then when you manipulate it a bit, it becomes, when you manipulate it, it would have become, let me just take you back. These are the mathematics that sometimes if you don't take it, you'll be a little bit confused. See this one here? On the right-hand side, you have 1 divided by 1 plus e raised to the power negative z. But what is a z? Check here. The z is a function. So the z is like our probability, y is equal to 1, giving the x, all equal to the beta naught plus the beta. So this beta naught plus the beta 1x, all of that, that is a z. That is this. That is this one. So wherever I see z, I'll put in that. But remember that z here in the actual segment function is negative, right? Check it. This is negative. So ideally, if I go down and I were to write this function, ideally, is going to be P of R equal to 1 divided by 1 plus e raised to the power negative z. And what is z? Z itself is beta naught plus beta 1 x. That is z. But I want to clear the negative. Yes, Wallace.
Sir, please, why is it negative in the first place?
Oh, this is a function. It's a function.
Okay.
It's like saying that one, you know that the Euler's equation, the Euler's theorem, which is 2.718. You know that pi. Whenever you are calculating the circumference of a circle, you know that pi. Sometimes you say pi is equal to that, or natural log is equal to that. Why is that in the first place? If I start proving that to you, why that is so, we are going into the pure mathematical, quantum analysis. You not even finish. So it's a function. It's a function that we are borrowing, and the function allows you to sit between 0 and 1. And our situation here sits between 0 and 1. Our response variable sits between 0 and 1. And so any function that can help me to continue setting between 0 and 1, I am happy. And this function does the work. So I'm just substituting this value. Okay, let me change the color here. I'm just substituting this value here into the z. That's it. And that's what I just did. But because this is negative, I need to rewrite the thing. And that would be another whole mathematical process. I've done it in one of my videos on the channel. You can check it. So one way to make this thing is to now rewrite the thing and then pick one of these to the top. So you take the e raised to the top before you give one down. Let me take you back here. Please, I hope you've written this. If you have not been writing these things, then obey it out. So let me just go down. So you see here, now you see that in order to remove the negative, okay, look down here. In order to remove, I rewrote the same thing, but there's a process of deriving that. Rewrote the same thing down here, this time without the negative, and then expanding the bracket out of it, and then bring the same thing up there. Now you sort out the negativity. So the probability of y equals to 1 given x is now this. This is the key. Ladies and gentlemen, this is what is known as the logistic function or the sigmoid function. Let me wipe up the rest. So when you see this one here, how we arrive at this is what I just showed. What is the E? The E is a mathematical constant, the Euler's number that I spoke about, 2.718. We know it already. And then your next question will be, how did we get the 2.718? Wallace, should I show you how we got the 2.718?
It's okay.
Maybe Kwame, you can show us how we got the 2.718. Kwame seems to have a lot of knowledge on false positives and false negatives. But these are all mathematical equations. We know it already. It's automatic. So guys, watch this. How will I be able to predict the probability that a particular person is defaulting or is not defaulting? The left-hand side. The only way is that if I know the parameters, if I know beta parameters and I know this one, I can just substitute and calculate the value, isn't it? That's all. Because I know the value of the 2.718. So no matter the beta naught, S is going to take a value that is going to fall between 0 and 1. We check, it doesn't matter, X can be 1 billion, 1 trillion, it doesn't matter whatever. This equation will force every number of the probability to be between 0 and 1. And that's all we wanted. We didn't want a situation where it to be above 1 or below 0. Just like in a regression, our task is to estimate the betas. And once you get the betas, boom, you will get the left-hand side, which is a probability. You got it. The parameters can be estimated, the betas. This time you can't estimate it using the the same principle in OLS. Remember the OLS, how we get to the betas? We minimize the error sum of squares. Do you remember that thing? Yeah. Okay. We minimize this error sum of squares. Okay. Subject to the beta naught and then the beta 1. We minimize it. Now, this error sum of squares is also called RSS, the residual sum of squares. And the residual sum of squares, if you can remember, okay, it was beta naught plus beta 1 x all raised to the power 2, something like that, if you can remember. You square it, and then you bring the sum here. So this thing is what we normally minimize in OLS. Now, please go and tell those who are not in class, I'm going to deliberately take attendance list. And I will penalize those that are not in the class because the number was large and now all of a sudden it's gone down. So I will penalize people who are not on the class. I'll be taking pictures of those that are in the class every moment in time. And I've been doing that. So just warn them. Okay. So instead of using the minimization of the error sum of squares, okay, we rather use something called maximum likelihood estimation. Now, the maximum likelihood estimation is going to be used to find the beta parameters here. The same way we normally do the similar one for the OLS. Okay. So, question. This is the data set that we have, for the default. Our goal is to predict the probability of default. The moment the thing is close to, 1, but it's close to 0, but it's never 0, it means that the person has got low balances. And then if it is close to 1, but never above 1, you see now all of a sudden people are joining the call, which means they deliberately leave the call. This is not acceptable, soldiers. So when you see this one, you can see that this balance is now sitting between 0 and 1 beautifully on the probability side, which is exactly what we wanted. Not this one, which is what OLS will give you. Now, if you go back to this equation, we can rearrange this equation. I can walk you through, but it's very mathematical. You can rearrange this equation, and then you'll get that. Because if you understand the principle of odds and log odds, you can now appreciate what we are about to do or what we are doing. Have you heard of odds and log odds? Okay. So to watch this, if you rearrange the function, watch this carefully. So I can cross multiply here, or I can multiply all through by the denominator. That will kill this one, and then this will now have a denominator multiplying the P of R. If you do that, you can now eventually convert that function into this. The rearrangement will lead to that. But let's talk about the left-hand side here. Now, this whole rearrangement and this, you don't have to worry about it. Now, let me ask you some English. Odds. What do we mean by odds? What do you simply understand by odds? The odds of achieving A or B. Hanan.
Say chance.
It's not exactly the chance, but there's something about chance in it. The odds of, what are the odds of, Argentina winning? What are the odds of Spain winning the game? So you see, 9 people have joined the call right now. That means you people were deliberately leaving the call. Sheridan.
Likelihood.
Which is the same as she said. So the odds compare the chance that an event will happen. Now, if the event happens, you write it down. Write it down. The odds compare the chance that an event will happen. That's the odds. It compares the chance that an event will happen. And if the event is happening, we call it success. If the event is not happening, we call it failure. So the odds compare the chance that the event is going to happen to the chance that the event is not going to happen. So what you are seeing here is the probability, the word chance, the chance or the likelihood that the event will happen is this. And the likelihood that the event will not happen is 1 minus the probability that the event will happen. This is the odds. This is what we mean by the odds. So the odds is the probability of an event happening divided by 1 minus the probability of an event not happening. This quantity is what we call the odds. And it always got to fall between 0 and infinity. Take note, it always got to fall between 0 and infinity. It has to be positive. Take note. It has to be positive. It has to be positive. That is it. George Disu, that is the answer. Okay. Yes. But you see, you normally don't want to, you don't want to take it from a linear perspective, because when you take it from a linear perspective, you got to take it from the log odds. We haven't come to the log odds yet. Right now, what I'm defining now is odds. The odds is a relative measure. The odd is a relative measure. It's a probability of an event happening, which is a P of X here, divided by the probability of the event not happening. That is the odds. Okay. You're going to see why we got to use the log odds, because the sigmoid function, you can see that is not linear. And so the interpretation is a little bit wahala. But I'll come back to that. We are going to think about or discuss why we have to move from odds to the log odds. Okay, that's all. Okay. Now, so for binary classification, which is what we are looking at, the odds of belonging to a class are defined as a ratio of the probability of belonging to a class to the probability of belonging to a class 0, which is what I just said. Okay. The probability of the event happening. The event happening is you belonging to, class 1. And the probability the probability of the event not happening is you belonging to class 0. And so this is the definition of that. If, for example, the probability of winning a game is 0.5, then the odds are 100%. The odds of winning are 1. Okay. The odds of winning are 1. What does this guy mean by English version? English version of what? David. All right, let's move on. But see, if you check this one, we can also prove that this left one, you see this one here, when you cross multiply, this whole thing goes to multiply this. Okay. And so we can say that the odd, remember this is the odds. This is the odds. This whole thing is the odds. And now if I equate this whole thing to PS, then if I want to find back the odds, guys, let me just show you. This is P into bracket X divided by 1 minus P of X. Okay. Very good. This is the odds. This that you are seeing here is the odds. Okay. Now, if I, and when I say this is the odd, if I say that P, this is equal to P of X. For it to be equal to P of X, I need to multiply this whole thing. I need to divide it by 1 plus itself. 1 plus P of X divided by 1 minus P of X. Okay. Where this 1 is for both of them. So this whole thing divided by this whole thing should give you this P of X. But what is this whole thing? This whole thing is the odds. So the odds divided by 1 plus the odds is the P of X. And that is it. If you go and run the formula, you see that you get back the same thing. But again, you don't have to worry yourself. You just have to take that. And that is the same point being explained right here. Okay. So I've spoken about the odds. What are the odds? The probability of an event happening divided by the probability of the event not happening. That is the odds. Okay. Now here is a challenge. We are going to convert the odds to the log odds. And once you convert the odds to the log odds, you have a logit. Why? Why? And here's why. Because the odds range between 0 and infinity. We said it before. And because logistic regression takes the logarithm of the odds, which is called the log transformation. So it will now scale the value, which is between negative infinity to positive infinity. It will now force it to behave more like a linear function. And that is why we got to convert the odds into the log or the logarithm of the odds. So we convert the odds to the log odds. Now, what I just said, some of you might not understand, but so let's get a bit slower. Probabilities. They are always between what and what? Probabilities. They are always between what and what?
0 and 1. Please.
0 and 1. Can you model it directly using a linear regression? Can you model probability directly using a linear regression? Absolutely not. But here we are dealing with probabilities. Now, the odds. Do you remember what we said they are between? The odds are between what and what?
0 and infinity.
0 and infinity.
So keep that. So that means that if it is between 0 and infinity, it means it's still not symmetric, isn't it? Because for the odds to be symmetric, it has to be between what and what? For the odds to be symmetric, well, you remember normal distribution is symmetric. Whatever is on the left side is a mirror image of whatever is on the right side. So for the odds to be symmetric, the odds should not be between 0 and infinity. It should be between what?
Minus infinity and infinity.
Perfect. But the odds can never be between minus infinity and infinity. What can be between minus infinity and infinity? The log odds. The log odds is always between negative infinity to positive infinity. And the log odds are linear. Hayaputa. They are linear. That was why I said, David, your question is good. They are linear, they are continuous. And that is perfect for regression. So what we are doing here is that we are transforming the probability 0, 1 into what? Negative infinity to positive infinity, so that we can use linear. That's all. That is all. So this monotone transformation of converting the thing using the log odds instead of the odd, okay, is called logit transformation. And by logit, we are talking about log it. And that word log is a natural log, by the way. Logit is a linear function in X, as you can see. Logit is going to be a linear function. So if you increase X by 1 unit, it does not change the odds. It rather changes the log odds by beta 1. So watch this. If you increase this, if it was normal regression, you say that 1 unit increase in X will change, or 1 unit change in X will change the dependent variable by the beta 1. But this one, we say that a 1 unit change in X will change the log odds. The log odds. Not that it will change the dependent variable, but it will change the log odds, because there are so many things in here, by the value of the beta 1. Write this down. This increasing blah, 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 blah. Write it down. Okay. So what we are saying is that our goal, what was our goal? Our goal is to find the coefficient, beta naught and beta 1. They are not known. They are not known. They are like simultaneous equation. They are not known. So we are going to use maximum likelihood to do it. What maximum likelihood is going to do is to find this beta naught and beta 1 for us. It's going to do that in such a way that the outcome, the predicted probability is close to 1 for those that are what? Defaulting, and then close to 0 for those that are not defaulting without ever exceeding the upper or lower bound. Now, this is beautiful. This is intuitive. But you see, the maximum likelihood estimation is not a small boy. For you to be able to use the maximum likelihood, you got to know the likelihood function. And for your master's degree that you decided to come to know, there is something called likelihood function. You have to hear of it, know it, and add it to your marriage. Because that marriage, after the marriage, you decided to come and learn this thing. This is the likelihood function. This is the likelihood function. A part of it is equal to 1. Look at it here. Part of it is equal to 0. Look at it here. Part of it is using probability of X, the chance of something happening. Part of it is looking 1 minus the probability of X, which is the probability of failure, the chance of something not happening. So it's a beautiful function. You see what this thing is going to do? This likelihood function is going to help us to find the beta naught and the beta 1 by maximizing. You remember in regression, what do? We don't maximize. What do we do? In regression, we don't maximize. What do we do? Of course, when you say minimize, I will ask you, minimize what? That's why most of you are quiet. Abigail.
We minimize the error.
Not just the error. The what?
The reducible error.
What is that? There's a full name for that. What is that? You minimize the error sum of squares. The error sum of squares, the residual sum of squares. Now, this likelihood doesn't do that. It maximizes, this function maximizes the likelihood function. And once you maximize the likelihood function, you're going to get the probability that the observed parameter is 0 or 1. Beautiful, exactly as we wanted. So we're going to select beta naught and beta 1 in order to maximize the likelihood of the information. That's it. Let's go and do that. This time, we are going to do that maximum likelihood estimation to find the logistic regression. So we're going to use a data set. So let's go back to the one we had before. Please go check your data. There you go. So watch this. We're going to still focus on pandas, NumPy. We are importing the library for building the regression model. We know those are the stars model. Then we are going to also do the same thing for the scikit-learn. That one is here. Now, we are still using this data set. Our one-hot encoding is usual. But watch what we have done here. What have we done here? Who can sense what we have done here that we didn't do before? Who can sense what we have done here that we didn't do before when we're doing the regression? In this code, there's something we have added. Yes, Ajay.
So we've encoded the student as well, but
Exactly.
the regression didn't do that.
Exactly. Ophelia, you are learning. I hope everybody else is learning like you. So we've encoded the student one. Okay. Now, our data set that we had, we are going to, so it's the same data set, but just that we have encoded the student one as well. And then we will now run the normal regression, this time still with balance, okay, add a constant, okay, like this. And once you do that, it's run, but I did not show the results yet. But if you can go and see this data set, if you still want to see this data set, okay, if you now run this data set, you see that now student has been encoded. Okay, that's it. Okay. Now let's fit the regression, the logistic regression model. We're going to do that with a circuit length. And we are going to instantiate the model. Okay. We are going to run the model using the default parameters. So I'm going to call the logistic regression log reg. Just calling it log reg. You can call it even your name. So in this log reg, we are going to fit the logistic regression model of both the input and the output, the X and the Y. You know what the Y is, you know what the S is balance. And then we will show the prediction, the predicted value. You see, we just want to show that it's not going to be negative. And then we'll print the predicted response, and then we'll get the confusion matrix. We'll look at the confusion matrix in detail next time. So this is a predicted response. Okay. This is the predicted response from the lower values and the higher values. I can show this. Let me just show something. If I decide to show all of this, all of the predicted response, this one will not come though, but let me just show this predicted response. So you see, the predicted response, okay, most of them are what? 0, 1, 0, 1, 0, 1, 0, 1. Well, but in this very example, you have 0, 0, 0, 0, 0, 0, 0, 0. Okay, the shape is 10,000, don't forget. But it's maybe that one is in there. Let me go back to the original one. So this is the same thing for that. But then we've also produced a confusion matrix, which I said will explain it. And that day, this guy will explain the confusion matrix to you, Kwame. Now, let's fit the regression model. Again, we are using the logit function. Okay, watch it. Y and X, we know what they are. Okay, we have the balance, which is the X. The probability of default is Y. We are generating the result, and we are showing the predicted value from the logistic regression. Watch it. Once you run this, boom, you get this. Optimization terminated successfully. Current function is given there. Iteration was 10. That's beautiful. So it's done multiple times. If you understand the maximum likelihood estimation, you got to iterate. The log likelihood ratio is provided. The number of observations is 10,000 is also provided. Today's date is also given, and today's time is also provided. Now watch this. Watch the constant. Okay, it's negative 10. Watch the balance. Okay, it's 0.0055. When you go and check the previous one and you watch the constant, it is this, and the constant was negative, blah, 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 and the balance was this. Do you see a difference? Obviously. Obviously, you can see that the balance has gone up. Okay, but we'll talk about interpretation though. The balance has gone up. Now let's go down here and watch this. We've made a point here. In fact, let me just show you here. Let me show you here because this is an interesting part. I've taken 4 pictures of the attendance so far. So this is it. This is the result that you would have gotten. Yep. So this is exactly the results that we also had here. What is so interesting about this? Well, first thing, you can see that any statistical package can fit a linear regression. Or it's not only this guy, Python, who can do that. R can do it. Stata can do it. Lambda can do it. You know, MATLAB, all of those things can do it. Even PAST, which is free, can do it. You go and look. I'm mentioning some of this, and you will need them. Some of them will do some great work for you. Again, PAST is free. Go and use PAST. It's called paleontological something. You know, and it's a click. It's not coding. Anyway, so what is the value here for beta? Beta now is 0.0055. Okay, it's positive. It's positive. And because it's positive, it means that there is a positive relationship between your balance and your likelihood of default. So it shows that an increase in the balance. So if your balance is increasing, it means that you are increasing the probability of defaulting. Does that make practical sense, guys? Does that make sense? Yes, past.
No, it does not.
Oh, it does not? Can somebody explain why it does or why it does not? It makes sense, Obaya. You are supposed to pay your credit balance. Okay. And then you pay your credit balance to what value? What value do we normally want your credit balance to be? Anybody?
0.
0. So if your credit balance is increasing, what does that mean? What does that mean? Yes, Stella.
But it means you don't like paying your debt. So you have the money balance to pay.
Oh, Stella, you have a very noisy background. Panel.
Okay, Prof. It means that when you're increasing your balance, the possibility of you not being able to pay back is per the model is 0.05%. So the more you increase your balance, the likelihood you will not be able to pay the likelihood that you default, because when your balance is too huge, it might exceed the income that you have, so you'll not be able to pay
Exactly.
the credit.
Because this thing is a process. So you can't say that the more the thing is increasing, you're not likely to pay. This is how they used to check the credit worthiness of a person. Okay, your balance is 50. No, clear the 50. You were borrowed that money, clear the 50. You didn't clear the 50. The balance now goes to 100. Then it goes to 200. Then it goes to 500. Then it goes to 1,000. You say, I'll pay. It goes to 2,000. I'll pay. It goes to 5,000. I'll pay. You declare bankruptcy. That's why you sometimes hear that a person is bankruptcy. This was the days of the credit crunch, foreclosures. You can't pay the house. And now you are complaining. Why will you go and take that loan? Then you are struggling. So your balance is increasing. And you see, it adds more charges because there's a lot of charge if you don't continue to pay. Okay. So that is why I say that. So this answer is practical. If your balances are increasing, you are likely to default to pay late. So a 1 unit increase in balance is associated. The word is associated. Keep it. Okay. We don't want to say, well, cause. Let's attribute association than causality. It's associated with an increase in, and the way you interpret it, you see here, we said it's likely. But when you were interpreting it and kasa using the unit, you say it's associated in the log odds. You see? Not the odds, but the log odds of default by 0.005 units. Remember that this value, this 0.005 units, that value alone, itself, is a big value because the balances are in thousands. That is interesting. So it means that it's associated with in the log odds of default by this interpretation. Guys, learn it because you will use this sort of interpretation in exams. In the exam question I've set, there was interpretations, plenty of them like that, where you are required to use the log odds in your interpretation. Okay. So let's go back here. Look at the p-values. Remember that the previous one, the p-values were similar like that. Now, because the p-value is associated with balance is tiny, it means it's significant, isn't it? So we can reject the null hypothesis, which says that it's insignificant. And we can conclude that there is indeed an association between balance and probability of default. The estimated intercept here is not so much interesting. You don't normally need it. It is for cosmetic purposes. Its main purpose is just to adjust the average fitted probabilities to the percentage of the ones in the data. We don't really talk about the coefficient, so don't worry, unless for predictive purposes. Okay, so now we got a model. Can we use the model to predict? Of course, you can use the model to predict. Mamma mia. Once you have the coefficient, you can compute the probability of default for any given credit balance that will come. So if anybody comes into the place and you say, okay, let me see your credit balance, and you check the credit balance, given the current model, that unseen data can now be used to predict. So let's do some prediction. Okay. We're going to do some couple of predictions here. What is our estimated probability of default for someone who now has a credit balance of 1,000? Can you predict that? Of course. How can you predict? The person has a credit balance of 1,000. Just put 1,000 here. X, whatever you see, X, put 1,000. Whatever you see, X, put 1,000. What is the beta note? We know the beta note. The beta note was a negative 10, blah, 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 blah. Okay. What is the beta one? We know the beta one. We know it is 0.0055. What is that person's balance? It is X. We know. Guys, you do these calculations in an exam. So put the 1,000 here. Whatever you see, X. That takes care of the numerator. And then you come to the denominator. Takes care of it. The rest is just taking a calculator. You know you can find this value easily using your calculator. And now, boom. That will give you 576. What does that mean? What does that value really mean? We'll come to that. And that is actually the predicted value. The probability of default. So this person has got a likelihood of defaulting. Now, the probability that the person will default, is it closer to 1 or is closer to 0? This value. Is it closer to 1 or is closer to 0? If you don't take care, you might think otherwise. Now, if it is closer to 1, then the person is likely to default, isn't it? If it is closer to 0, yes, Panel.
I was saying it's closer to 0.
Yep, I agree. So the 1,000 is not a big deal. The credit balance of 1,000 is not too much a big deal. Let's look at 2,000. You check the 2,000, look at the credit balance of 2,000. It's 0.5, almost 0.6. So now question, is this person likely to default or is not likely to default compared to the other person?
It's closer to 1, so it's likely to default.
Exactly. So whereas this person is unlikely, relatively speaking, unlikely to default, this person is likely to default. Now you can predict the probability of any person that comes on board. Now, remember that the coefficient the independent variables, there was a student. That student was an independent variable. It was a dummy variable. We didn't include it, but we can do it. We can include it now. So let's go to the model and include the coefficient because we're dealing with only credit and balance. But let's do something else. Okay, let's add the predictors. Okay. So this one, I'm just doing is that we are just adding. So watch it. The data is this, but this time we are doing it for student, only student though, only student. We are not including balance. We are not including income, only student. So we are saying that what if a person is a student, does that affect in any way the probability of default? What if a person is a student means, what if a person is a student relative to a person who is not a student? As I said, when I say, what if a person is a male? I'm actually saying that what if a person is a male than a female? That's what I'm saying. What if a person is a student means, what if a person is a student than non-student? That's also what I mean. Okay, let's run it. This is the result. This is the result. Now there's a problem. There's some kind of interesting problems and interesting things here. Okay, so you got a value of this. The fact that it's positive means what? You can tell us. The fact that it's positive alone, what does that mean? Yes, Kenneth.
So please, I think it presupposes that if a person is a student, there's a higher likelihood that the person will default.
That's it. Job done. Job done. This is a result. So the coefficient associated with the dummy variable is positive, and the associated probability is significant. You can see that here. It's less than 5%, which shows that the student tends to have higher default probabilities than the non-student. So if you are not a student, you are likely to be working and therefore making money, and so you don't need money from a credit card company. I'm working. But students are not working much. They are broken. So Let's talk about a new student coming. What is the probability that the student is going to default if the person is a student? Well, you substitute the value there, 0.4049. Put it wherever you see the X. And now you predict. This is 0. What does that mean? This student is not likely to what? This person is not likely to what? Is this person likely to default or not likely to default? It's not. Then we talk about this second person, and you can see that. So it doesn't necessarily. Okay. Well, it depends on the sort of person who came. So when you take only this one, it might not give you the full picture. You got to take other factors into consideration. Are you with me? So you can't just pick one thing. Okay. Sometimes you have to look at other factors, and those other factors might deal with that. So why don't you combine all of them? Why don't you put all the factors now together? Everything. Instead of just student, instead of just income, instead of just balance. Let's drop everything into the picture. Boom. So now we're going to look at multiple logistic regression with binary response variable. Now, remember, the dependent variable that we looked at was binary. Okay. But then we are going to look at a situation where the independent variables are many. This is the log odds that we spoke about. This is the log of the odds, And now there are multiple independent variables, multiple predictors, multiple independent variables. The probability of default is going to be like this, multiple. Now we're dealing with multiple independent. Guys, when you are writing your longest and you are doing logistic regression, which I guarantee you, if you are doing classification, you got to do logistic. If you are doing customer prediction, chain prediction, loan default, all of those things, all of you who are doing that, you're going to use this model. You got to write a mathematical model generally and specifically. Write it down somewhere. Write a mathematical model generally or specifically. Some of you are doing your models and you don't know that you have to write the models generally. This is a general multiple regression model. But when it comes to the specific one, you have to fit in your X with the variable. So suppose your variable is income, you put income here. Suppose the next variable is balance, you put balance here, you put all of them there. That's what I mean by it. So let's go to multiple. Okay, multiple independent variables. Let's go to our model. So logistic regression, several variables. So remember the balance is there, the income is there, the students is there. So this is all the independent variable. All of them. Here's the result. Run this, show the head of the data, run this final one, watch it. I'm putting all of them together. All of them. They are all X, and I've added a constant. How do we know that they are all X? Well, we showed them here. You say them, drop all of them. Add all of them except the default. So default is a dependent variable. And now you see that the result is showing everybody. Everybody. Let me show you this really. So this is it. What do you see about the student? Do you now see that student is now negative? Let's go back to when we did the student. Student was positive here, isn't it? So what do you see now? Student is what? Negative. Remember when we said that instead of doing one by one, you should put them together. Because other than that, some of the things will not make sense. So I have a question for you. Question. Why? What's my question, Craig? Why? Okay, I'll come to that. So first, look at the p-value for balance. It's less than 5%. Look at the p-value for student. It is significant. So it shows that each of these variables is associated. It has association. Whether it's positive or negative is a different thing. It has some association with a probability of default. Cool. But the coefficient of the dummy variable is negative. That's why I've highlighted it. What I was going to say, what does that mean? I think I should ask you. What does that mean? Since the coefficient of student is negative, what does that mean? students are what? Are they more likely or less likely to default? What do you say? Are students more likely or less likely to default? It means that students are less likely to default than non-students. That is what it means. Okay. So why is the coefficient?
So can you please explain that? If you say less likely, looking at the coefficient of the negative, is that the reason why you say less?
If you're a student, because it's negative, okay, if you're a student, it means that you are not likely. You would default, but you're not likely to default than if you are. We know that it shouldn't have been negative. That's what I'm saying. We know.
Okay.
Okay. It doesn't mean that it's perfect. That's why my next question is, why is it negative when before it was positive? But what it currently means as it stands now is that students are not going to default, more or less. They are less likely to default. And that those who are working rather are rather going to what? Well, they are all going to default, but then the students are less likely to default than that. And the question is going to be, why? Why is it negative in the first place? Why? Why do you think so? So pay attention here. Oh, yeah, I like Kwame. Kwame, go ahead.
So can we say because of the other factors like balance and income?
What have they done?
So based on, you see, initially we did it only with students, but right now you're adding other factors like
Yeah,
balance
but
and
if we
income.
have added other factors, that is true. But why? Why? Because in life, the other factors are also existing in real life, right? I agree. But if you tell me that because we've added other factors, yes, but practically why? Penal.
I'm thinking that for a student, looking at the student's income, he's not going to increase his balance beyond his threshold or like the income that he has, knowing that he has limited source of
I love
income.
this. Guys, it's not the numbers, it's understanding the reasons behind the numbers. That is the key. So all the time when you get your results, sometimes I get my students doing, see, doc, I want the thing to be significant, but it's not significant. And I say, you want it to be significant, and it's not significant. Why do you want it to be significant? You can't force the thing to be significant when it is not want to be significant. Find out why it is rather. So, fantastic, Penel. So the coefficient for student changes from positive to negative. In that simple one, but then in the current one, it's negative. Yes, boy.
Prof, please, can Peno repeat what you said again, please?
What did I say? I forgot.
No, Peno's response, if you could repeat it again.
I've forgotten what I said. What did I say?
He meant Panel should repeat his explanation.
Panel. Okay, Panel. Okay. Panel, repeat.
Okay, sir. So I was saying that for a student, he's not likely to increase the balance because the more you increase your balance, you're going to default. So looking at the income that a student will have, his balance will be lesser. So therefore, not having the likelihood of default. Unlike those who are working. Those who are working have like expected incomes and they know that they can increase their threshold. So they will increase their balance and then in the long run, they have the high probability of defaulting.
Does it make sense what he's saying? Obriabo.
Yes, please. Yes, please. I was writing it down.
So here's the thing. In that simple one, it was positive. In the multiple logistic regression here, it's negative. Why? And the answer is because of confounding by balance. Write it down. Because of confounding by balance. Because of confounding by balance. Now, in the model that was using only the student, students may appear more likely to default. We know that, the first one, because on average, students tend to have higher credit balance. But since higher credit balance strongly increases the probability of default, we know that. The student variable at that time indirectly was capturing the effect of the balance. But once balance and income are included in the model, as you can see here, the student coefficient shows the effect of being a student while holding a balance and income constant, which is what he was saying. Now, you know you're a student. You know. Sometimes when you're going to school and you're from a village, your parents, your uncles, your nephews, the chief, they will all call you and they'll tell you that Adwa. How many times have we called you? Know where you are coming from. Don't go and be doing shakalabonto. Know where you are coming from. Have you heard of that word? My mother used to say to somebody, do you know the meaning of those of you can speak Tree? Can somebody explain the meaning of when somebody made me who? None of you can understand. Should I move on? Okay.
So please explain so that some of us can understand.
So you don't understand.
Dog,
Yes,
it means
I
stay
understand.
out of trouble.
Live by your means.
Live by your means. Stay out of trouble. Don't go and cause any problem. You know, when people are demonstrating and doing hey, stay in your corner. That's what it means. Yeah, somebody was calling me.
No, but those statements worried some of us all.
That's morality issue. I'm talking about multiple logistic regression matter.
Be guided.
Be guided. There's nothing wrong with that. If you are living in a poor country and you go to a rich country, you will see the way people are spending. If you don't take care, you will go and spend like they are spending because the credit card is allowing you. We are warning you. I said that those things make people what? It is contextual. What we are saying is context-based. So under that comparison, the students with the same balance and income as non-students, they are now estimated to be less likely to be default now. So note that before the adjustment, the students appear more likely to default. But after controlling for the balance and income, because you know your income, you know your income, you are not likely to default. You know your income. Remember, we were brought income here. You know your income, your pocket size. Draw sokora to me easily. You know where you are coming from. And he was saying what? We should not say that. Otherwise, people will what? Masa, Warren Buffett will tell you that he still buys KFC, even though he's a billionaire. So you got to learn principles of discipline. That's the word. Discipline. Frugality on your credit card is indiscipline at the highest level. So this reversal occurs because the student status and the balance are related. That's what it means. And the balance is the dominant predictor of default. We know that if you check balance, you see that it is 0057. It's a dominant predictor of default. So this is called confounding, and it's closely related to something known as Simpson paradox. Go and check Simpson paradox. Cosmos.
Look, is this confounding different from interaction effects that we learned?
Yeah. It is related. Not exactly, it's related.
Okay.
Yeah. And this graph is also showing you a similar one. Everything we said is in there. Students tend to have a higher balance than non-student. So their marginal default rate is higher than the non-student. But for each level of balance, the student default less than non-student. You can see that. So clearly, that is it. Now, let's make some predictions now. What is our estimated probability of default for a student with a credit card balance of 1,005? And now he has an income of 40,000. Can you drop it in the formula? Oh, yeah. So let's start. So here, remember that it's the same formula. The only thing is that now we have added what? See, this plus. Okay. At first, it was only this plus. But now, we have this plus. And then we have that. So you see, we have added everything. So the last one there is a student. Okay, so this one means your person is a student. Okay, and then this one is the balance. So this is balance, this is income. So the person's income is what? 40,000. Where's the 40,000? I can't see the 40,000 here. Oh, this is it. Oh, where's the 40,000? Yeah. No, because this is 40 because it's in thousands. Okay, so it's 40. Remove the 1,000 from it. Okay, but then the 15, the balance is exactly put there. So that one is 15,500. But then the income was shrunk to 1,000. So if you substitute all of this, you're going to get this. So when you take everything together, now you've taken everything together, a person with an income of 1,005, an income of 40,000, a balance of 1,005, and the person is a student. Is this person likely to default or not default? Quickly. Quickly.
So not default.
Thank you. Next one. What is up? You should be able to calculate this one. If I tell you to calculate right now, some of you might take just 2 minutes to do it. Others might take maybe 2 hours to do it. So learn how to calculate. We're not going to delay that. So this time is for the non-student. So the non-student, nothing, everything remains the same. What is the only thing that changes here? Non-student, what is the only thing? Only one thing will change. What is that?
So please, the 1 will be changed to 0.
Perfect. This 1 will go to 0. And that's it. So it's like this whole part will be gone. And now you are good. You are good. Opele, you are very good. And that will be 0.1. So if a person is a non-student, you see, all of them are likely to default. All of them are not likely to default in this contest. But then you can see that the student is more not likely to default than the non-student. Do you see that? That is what the value here is showing you. Okay, because this one is closer to 1. But both of them are less than 0.5. So that's the point I said here about the 40,000. So I said that the coefficient estimate is multiplied by 40 instead of the 40,000 because the model was fit with income measured in units of 1,000. In units of 1,000. I hope you are getting this. It's exciting, isn't it? Or it's not exciting? Is it not exciting? And family.
Very, very exciting.
Yeah, it's supposed to be exciting. Let's go to the last one for today. All of this logistic regression, we deal to binary logistic. But then sometimes you can see that there will be more than 2 classes, 2 groups. Today we are dealing with default and non-default. What if you have a situation where you have stroke, drug overdose, and epilepsy? 3 dependent variables. Or let's say that you have ice cream. Okay, and you want to look at the factor that will determine whether a person will buy vanilla, chocolate, butterscotch, or blackcurrant. Which one is the person going to buy? Well, it depends on the person's gender. Ladies might buy blah, blah, blah. Okay. I didn't have strawberry, but if there was strawberry, men and women, who will buy strawberry?
Women.
Good.
Women.
And then age. Old people and young people, who are more likely to buy vanilla? Okay. Let's go to strawberry. Old people and young people, okay? Let's say they are all women, old and young. Who is more likely to buy strawberry?
Young.
Young. Okay. And sometimes occasion, whether it's a wedding or blah, 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 will determine. Sometimes the happiness level and all of that. Okay. So in this case, the K is positive, greater than 2. It's very easy to extend this to this 2 class to 3 class or 4 class. And now we are no longer in binary logistic. We are now in multinomial logistic. Multinomial. Very good. There are some assumptions. For this to work, first of all, the dependent variable must be nominal or ordinal. There shouldn't be any multiple among the predictors. There should be no outliers. These assumptions are standard. They're supposed to be standardized. So in the nominal case, logistic regression with more than 2 classes, let a class K be the baseline. So watch it out. Nothing has changed much except that in this case, Y is equal to K, given X is something else. And now so you just need to have a baseline. It's just like the normal independent variable. Remember when you have an independent variable and you have 3 religions like Christian, Muslims, and Buddhists. Once you take the Buddhist as your dependent variable, you are saying everything. So whenever you say Christians, you are saying Christians relative to what? Buddhist. Whenever you say Muslims, you're actually saying Muslims relative to Buddhists. So Buddhist becomes the baseline, the reference category. So the same thing here. It has to be the reference category. Okay. And then once you have the reference category, you make the whole thing acceptable. So the dependent variable can be 3, can be 4, can be 5. But the key point is have the reference category. And when you do that, and you are writing your log odds is now going to be this. Remember, this side is going to be the same thing as before. The only thing is that when you have multiple dependent variable, you don't have only this, but you have the dependent variable. Sorry, you have the baseline. So watch it. Note the difference between K in the numerator and K in the denominator. Okay, so the log odds between any pair. So you are checking any pair of classes in the linear. It's linear in the features. Of course, this whole thing here is linear. But I can be saying that if the baseline is Buddhist, I can say that the probability that a person is Buddhist relative to the fact that a person is Christian is affected by the following. That's how you say it. That if you are writing the logos, that is exactly how you'd have written it. Multinomial is quite tough. It's quite tough. In the nominal cases, the logos is between K and K prime. Okay, so you have something like this. So in this example, with the 3 classes of stroke, overdose, and epilepsy, if we set epilepsy as the baseline, the reference category, then we can interpret the intercept for the stroke as the log odds of stroke versus epilepsy, given blah, blah. Exactly what I said, given the independent variables. Furthermore, a 1 unit increase in any of the independent variable is associated with the coefficient of the stroke increase in the log odds of stroke relative to epileptic seizure. So anytime you mention one of the dependent variables, it is in relation to the baseline. The baseline. If you understand a lot of the way you interpret independent variable for dummy independent variable, this one is cool. It's the same thing. I'm not going to look at the nominal classes here. The ordinal. Let's look at the ordinal. So ordinal classes are classes that are numbered. So you have them ordered meaningfully. The difference between nominal and ordinal is that nominal is meaningless. For example, if you take religion, Muslim, Christian, you can't say that one is better than the other. Relatively speaking, you can't. Okay, but ordinal, if you take lecturer, senior lecturer, assistant professor, you can rank them. So that they are all English words, but then, so in the stock recommendation, there are 3 classes: buy, hold, and sell. This can be treated as ordered. Buy, hold. When the number of the classes is large, typically more than 5, see, now we are talking about more dependent variable. We can treat the dependent variable as continuous. and perform multiple linear regression. Okay. When the number of classes is just 2, the logistic regression described earlier is used. So when you have so many, like political parties, then in this case, you can code them and rank them, and use some coding for them, and you can run your multiple linear regression in the process. Very good. Then logistic regression with 3 classes, okay, and 2 predictors. There are several ways to extend the binary case, all of them. All of these are different ways. An example is the proportional odds. So you're using percentages or cumulative logic method. All of these, so let's take, for example, in a stock market recommendation. I'm not so keen on this. That's why I'm moving slightly fast. In a stock market recommendation with 1 predictor, X, and several groups, 3 groups, where the groups are 1 for buy, 2 for hold, 3 for sell. If you use a cumulative logic model, the probability estimators will be the probability that Y is 1 or less, or 2 or less, because we have 3 different classes. So it's no longer going to be between 0 and 1, because there are 3. And how do you write the log odds? The same thing. You have to write the logic for the buy, okay, the log odds for the buy. You have to write the logic for the buy or hold, the log odds for the buy or hold, okay. You got to write the logic for both of them, taking into consideration the other. So that is how you work that. And then if it is an ordinal classes, the same principle. Once the coefficients are found, the class membership probabilities cannot be computed. Drop them there. Once you know the x's, you already have the beta values, you substitute, and you can use this for predicting. An example will do. So what's the difference between the nominal versus ordinal? The key point I've already told you. The estimated logistic model will change depending on whether the dependent variable is coded as ordinal or nominal. I like it to be nominal for binary logistic regression, and then ordinal for multinomial logistic regression. Okay. The accident data will give us a clear idea of this. Watch this. The accident data is a very practical one. We're going to end with that. So we have 42,000 actual automobile accidents in 2001 in the United States. They are involved in one of these 3 levels of injuries. So when there's an accident, no injury, injury or fatality. For each of the accidents, so this is 3 classes. For each of them, extra information is recorded, such as the day of the week. That's an independent factor. The weather, the road type. A company might be interested in developing a system for quickly classifying the severity of an accident based on an initial report and associated data in the system. Some of them will rely on the GPS-assisted reporting. Now, the idea here is to predict whether an accident just reported will involve an accident that is causing injury, no injury, or fatality, using just two independent variables, but the independent variables are nominal: alcohol and weather. For each of the predicted, you're going to code as no. No means that it is not involved in the accident. Yes means that it's involved in the accident. Now, so this alcohol is coded, it's a dummy. Alcohol is no, which means the person was not drinking alcohol when the accident happened. Or 1, the person is drinking alcohol. Or yes, the person is drinking alcohol when it happened. So you're going to do that. So let me quickly take you back to the model here. Now, before you can do this thing, there was a certain library called MORD, that you're supposed to code. If you could code that, If you have that thing installed, then it helps you to be able to run this very model that we are talking about. So it requires that you have it clearly installed. So most of you might not, if your internet is not there with you. Okay. is what do you call it? What's the name, cry? If you have a very good internet and you can follow, that's good. Okay. But if not, I don't know. Some of you will have it. Some of you will not have it. So it depends. So you check. Let me give you some information on mod. Mod. You know. Python. So if you are predicting variables that are discrete and ordered, like movie rating, like the one we just have, accident, 1, 2, 3, it will merge seamlessly the standard scikit learn using the familiar methods. So that is, you have to use the pip install to install it first before it can work. So I did that here. And then after that, it can go. Because if you don't do that and it come here, okay, it will not work. So you have to make sure that you've coded that. So I'm going to run that assumption that is there already. I'll now load the data. I'm going to just show the first 8 part of the data. That's it here. As you can see that I've coded all of them. Now, let's indicate the response variable. The response variable is markserv IR. The predictors we are using is alcohol and weather. Okay. Now, this response variable that we are talking about is an accident, whether it is injury, no injury, injury or fatality. Okay. So this one is the accident. Okay, the types. And then that is going to be the response variable. Now, let me show you here so that you see the accident. That's the last one there. Okay, so this last one is the dependent variable. That's what we are dealing with. Okay, so you now build a nominal logistic regression using the solver method. This is a nominal logistic regression that we spec. You create the logistic regression model for the solver. You get the coefficient. You run your probability of the logistic. You get your results. As always, as usual, you will get the coefficient. These are the coefficient for the intercept. Okay. And then this is a coefficient for the two, alcohol and what was the other one? Weather. Okay. Alcohol and then the weather. And then you will get the actual versus the predicted for each observation. And then you can go ahead and then run this final result for the model. And you can get for the ordinal. So if you check here, we've run for the ordinal logistic regression. It gives you the theta and the coefficient. And then here was the nominal logistic regression. Nominal, you don't use the coding. Ordinal, you use the coding. So I'm just going back here to show you the interpretation of the result. So this was the code that I ran, the code that I ran, the code that I ran, the code that I ran. And that's it. Okay, let me just go back here. We'll do the deeper interpretation of each one of this next week. But please go and run these two models for the ordinal and the nominal logistic regression and get the details. Because my colleague has ended at this section here, I want to just end at this section here so that there is harmony instead of disharmony. But we'll look at the details of it. Let me take you back here and show you this. If you check for the nominal and check for the ordinal, okay, the key is your ability to interpret the coefficients. That's the key. Remember that the coefficients are dummies. The independent variables are dummies. So you will say that whether or not there was weather, okay, if there was weather than not, or if there was, what's the other variable apart from weather? Alcohol. If there was alcohol, okay, the predicted value of of no injury, injury or fatality is that, so the predicted value is higher or is positive, or there was going to be an injury if there was an acid, an alcohol, or there was going to be no injury if there was no alcohol. So those are the ways we are going to interpret it, but I'll do that interpretation rather next week. Ladies and gentlemen, that brings us to the end. Let me just go back here. Somebody has been repeating what I've been saying on this thing. Ladies and gentlemen, that brings us to the end of the entire what?
Kabudo.
Entire Kabudo. Any question?